uniform. What does it mean for things to be uniform? Rebecca. The same. So if things are uniform, that means things are the same. So, I mean, this is why, uniforms are a big deal in school, because everyone looks exactly the same. Nika, would you rather lose a hand or a foot, and which one? Which one? Which hand? My left hand. So things are uniform, things are the same throughout. So we're talking about uniform motion. This means the motion is the same. Not necessarily the same between the two objects, but the motion for an individual object is the same. So what are some ways that your motion could be uniform? What does that mean if your motion's always the same? Danny.
You're always walking, or you're always moving at a certain pace, or...
Okay, so your pace stays the same. I like that. Another word for pace is what? Speed. Love it. Your speed stays the same. Another word for speed is? Sorry? Pace, yes. I like it. I was looking for a word that starts with a V. Velocity. Sometimes we use those sort of words interchangeably. You'll learn that that's not actually true later. What else so if your speed stays the same, what else must be true for your motion to be uniform? There's one more piece to this. Absolutely. Your which? What do you mean? I feel like rhythm's kind of like speed. What about time? Okay, so your pace stays the same for a given length of time. I'll add that in there. Of time. There is one more thing that is necessary for you to have uniform motion. Yeah, Ty. The direction, what about it? The direction also is not allowed to change. Absolutely. Cool. So these are the two pieces that make motion uniform. Your speed's got to stay the same for a given length of time, and your direction must also stay the same. There is a formula that relates these three things together. Your speed, your time, and not direction so much as another D word, distance. Does anyone know what the formula is that relates these things together? Yes?
Is it time over distance or speed over distance? My dad said something about it like 3 years ago.
Your dad said something 3 years ago and you can't remember. That doesn't surprise me at all.
But it's something like something over something.
So it is something over something. We're dividing something by something. Bam. Speed over distance.
Is that right?
No, that is not. Okay, let's analyze units here for a second. When you talk about your speed, what units do we typically talk about your speed in? Kilometers per hour. So when things are kilometers per hour, what does that mean? How many kilometers you travel in a given hour. So sorry? Yes. So your distance over your time, your kilometers per hour, is going to give us what then? Speed. You'll see different variables. Some classes use R for rate, some will use S for speed. Both of those letters are garbage to represent speed. The letter we're going to use for speed, Chelsea, is V. So V for speed equals D for distance divided by T time. When we use V, then we're not actually talking about speed so much as velocity, but they are certainly very related. This is one of the formulas. There are two more, But the other two formulas are just manipulations of this formula. If I want d equals, how am I going to use this formula to get d by itself? It's going to be v times t, because I'm going to multiply my times up here. The times are going to cancel, and then I'm going to get multiplied time on this side, and I'm going to get d equals v times t, which kind of makes sense, right? If you're going 50 kilometers per hour for 2 hours, how far have you gone? That was an actual question. 100 kilometers, right. 50 kilometers per hour times 2 hours. I asked the question like, yeah. So I assumed we were good, but I want the answer too. And then the last one is isolating either one of these things for t. Now, this is the easier one to isolate for t. Why? Because, well, not because it's already multiplication, but because where is the t? It's not in the denominator. When it's not in the denominator, it becomes easier to deal with. So we're going to isolate this equation right here for t. To get t by itself, what do? That's going to be d over v. So we're cool with this dot being multiplication, yes? Okay, I know I've asked you that question before, but I'm just bringing it to your attention that that's what I'm doing there. And my t's, I am drawing them slightly fancier. That's bothered some students in the past. The uniform motion problems, we are going to employ some of the similar techniques that we've looked at before. Before we do this, there is one more kind of formulaic technique I want to show you here. When you have a formula like this that's 3 variables, and they're all kind of nicely related to each other, there is a technique you can use that looks like this. Hands up if you've seen the formula triangle before. Angel, where? In 8th grade, what? This is the symbol for the Deathly Hallows. Ty. Is it like science? What did you do in science? To find volume. Oh, use the triangle for density and density, volume, and mass. Oh, interesting. Yes, this is same application. You would use it in science. Do you do it in science 9 or is it science 10? You guys use circuits in science 9? Yeah. You're doing that next. How many of you have done? Did you use the triangle for voltage, resistance, and current? It's the same idea. Okay. So it depends on your science teacher. Some like to use these techniques, some don't. It is a neat little tool just to help you remember these things because I'm not giving you a formula sheet. How the triangle works is this. We're going to look at this this expression here. This one gives me a v times t going on here. So what I want to do is I want v and t to go beside each other in the bottom of the triangle. What did I say? Did I not say speed? Did I say something different? Okay, so v and t. V is velocity or speed, which are not actually interchangeable, but we're going to use them interchangeably until you hit physics 11. V and t go beside each other. They multiply together. That's the implication when you have 2 variables side by side with no symbol in between them. And then d is going to go on the top here. Setting it up like this is going to give us all of the other formulas. If I want to solve for my velocity instead, what I'm going to do is I'm going to take my finger or my pencil or whatever. I'm going to cover up v, and then v is going to be d over t. Or if I want t, it's going to be d over v. Or if I want d, it's going to be v times t. So you cover up the one you want, what is left, and the way it is written will tell you what to do with what remains. Now, it's never going to be this easy, because why would it be? What we're going to do is we're going to look at a couple different styles of problems. This first one is an example of what I call a catching problem. Bless you. And a catching problem is exactly what it sounds like. One person thing object, whatever, has to go catch another thing that has left earlier. So, you leave your house riding your skateboard to school. We're going to assume that for the sake of this, it's a straight shot, which is not necessarily true, but for this, we'll assume that your speed stays the same, you make every light, all that jazz. You maintain a speed of 3 kilometers per hour, which for a skateboard is actually pretty slow. Your brother, now this is the part where some of you be like, nah, this will never happen. Your brother sees that you forgot your big project at home an hour after you left and leaves to catch you on his bike. He is desperate that you... Yeah, see? Well, for the sake of the problem, let's assume that your brother actually cares about you. Your brother leaves on his bike at a speed of 15 kilometers per hour, assuming he's bringing your project with him. And assuming the same things for him, he makes all lights, he's following the exact same path you are, all that jazz. Question is, when does he catch you?
How far away is the town?
No. He's not meeting you at the school. We're assuming that you and he have not you haven't made it to school. Yashvi. Hello, Yashvi. Yes. Not one of these two. You have to take one of the two from in there. Yeah. Anna and Amy are being protective of their computers. They need it for their spirit day. That's tedious. I'm sorry. Okay, so you have not made it to school. You are the world's slowest skateboarder. You've been skateboarding for an hour. You're still not there. You live somewhere in the country. It sucks. I see a hand back there. Yes, Carolyn. Yes. Let's prove it. So, one of the techniques I'm going to introduce to you guys here is the employment of yet another chart. Okay? We like charts. We want to use a chart to organize thoughts. Okay, so just like before, just like the age chart. So before we had the age chart, it was the two people, it was their age now, and it was their age then. Or we had the money chart, the number of the coins versus the value of the coins. This one is going to be a chart that relates to two people with their distances, velocities, and time. So the chart's getting a little bit bigger. So let's use it. And you might eventually be like, I don't need this stupid chart, and that's great. But I want to start us with the chart. So we have you, and we have your brother. For each one of these, we're going to talk about dv and t. What can you tell me about any of dv or t for you and your brother? Rebecca, give me one thing.
We're going at 3 kilometers an hour.
So this is your v. V is 3 kilometers per hour. Okay. And Danny, give me something else.
Same thing, but for the brother, it's 15 kilometers per hour.
The brother is 15 kilometers per hour. Okay, that's cool. What else do we know? Rebecca. You left an hour ago, and your brother's leaving now. So how does that going to show up in here? Now, I want to make a note here. This T stands for the time you have been traveling. Okay? So how does the fact that your brother, that you've been gone an hour and your brother's leaving now, how can we figure out a way to represent that in a chart like this? Using a variable for perhaps one of them. I'll give you, okay, well, someone give me a variable to represent the length of time someone's been traveling. I don't care who. No, at the 1 hour mark, your brother leaves. Like, you're traveling more time than that. An hour plus x. So who's x then in your... Who's going to be the variable x? I'm assuming that's what you're using. You want your brother to be x? Okay. If the length of time your brother has been traveling is x, how much time have you been traveling? Yeah, this length of time plus the hour you've already been traveling. Good, Nika. Then if we had called your time x, then your brother would have been what? X minus 1. Because if you've been traveling for x hours and your brother just left, you have to subtract the hour, the additional hour. He just now started. So this is arguably the trickiest part here. Once you've got an expression for one of these things and values in another spot, so we've got like values here for the velocities, we've got expressions for time, what we're going to do is we're going to use the correct formula to plug in this information into the remaining column. So I want an expression here for D, for both of these things, using this information. Yes, Danny?
Like it's speed times 2, so it's 3 kilometers per hour times x plus 1.
How do I write that?
Oh, what do you mean?
How do I write 3 times x plus 1?
Oh, right.
Thank you. Right, because distance is velocity times time. You see that right here. So my velocity is 3, my time is x plus 1, so we're going to multiply these things. Same thing down here. Your brother's distance traveled is going to be 15x. Cool. And what do you know is true about your distance and your brother's distance? And this is true of all catching problems.
They're not the same. I don't know.
Your brother and you, assuming the two of you live together, and he has now caught you, if he follows the same path you did, what is true about your distances? They're the same. They are the same. If you start at the same spot, you end at the same spot, and you took the same path, your distances have to be equal. So these two expressions now must be equal, and this right here is true for all catching problems. This is the key to the whole problem, that your distances are equal. So this then is going to become the expression that we're going to try and solve. We're going to set this thing up here. 3 bracket x plus 1 equals 15x, and now we solve it. Where x represents the length of time your brother has been traveling. So we're going to distribute this thing in. We're going to get 3x plus 3 equals 15x. We're going to minus 3x. We're going to minus 3x. We're going to get 3 equals 12x. We're going to divide by 12. I'm just speeding through this because this is the part y'all know how to do. So 3 over 12 is 1 over 4. 1 over 4 what? What are the units on that value? That is hours. Okay, cool. So the question, have we answered the question? No. When does he catch you? He catches you at when? 15 minutes after he leaves. So let's get rid of this word at. That was a dumb word. Catches you 15 minutes after he leaves. This is different than the answer Carolyn gave us. Why? How else could we have quoted this? She said it was an hour and a quarter.
Yeah, that's right.
Okay, so that would be after you left. So then Carolyn's answer is he catches you 1 hour, 15 minutes after you left. Either one of these is totally acceptable, but this is why it becomes now so important to give us words and a context for your answer. Because x equals 1 over 4, that's absolutely correct. But Carolyn's answer, x equals 1.25, also totally correct, but from a different point of view. It's like Obi-Wan Kenobi at the beginning of... No, it's like halfway through Empire Strikes Back, or is it the... No, I lied. It's Return of the Jedi. When he's like, what I told you was true back in the first movie, from a certain point of view. Well, yeah, both of these are true. From a certain point of view. Yeah, your father, in a sense, was killed by Anakin Skywalker, or whatever. 15 minutes after he leaves versus 1 hour and 15 minutes after you left. Either one of these is correct. Danny, you had your hand up.
I don't anymore.
You don't anymore. Cool. Fun? We like it? Nice and easy? You can do it on your own, right? Flip the page, just do another one. This is a slightly different style of problem. Okay, so we're going to get rid of this. So we're going to set up our own table. A plane leaves Montreal for Calgary, a distance of 3,000 kilometers, traveling at a speed of 550 kilometers per hour. At the same time, a plane leaves Calgary for Montreal at 450 kilometers per hour. So this one's a little bit slower. How long until they pass each other? Sorry? We're going to set up our own. Because I like writing it in a slightly different order and I use slightly different variables. So, here we go. What are the two planes? What do you mean Calgary and Montreal? They're both... One's leaving from Calgary, okay. So we have the Calgary plane. And we have the Montreal plane. DVT. What can you tell me about any of these variables for either of these planes? Someone other than Danny or Rebecca. Because they jumped all over the first question. And Carolyn solved the first question. Yes, I see that hand. Is that true? What's the question asking us to find? Where they pass each other. So what we've got here is this. Yes, the distance from Calgary to Montreal, the total distance is 3,000. But they're going to pass each other somewhere in the middle. Are they going to pass closer to Calgary or closer to Montreal? Why? Yes, it's going to be, and I'm hearing a few different sections of the classroom figure this out. Because the Calgary plane is traveling slower than the Montreal plane, they're going to meet closer to Calgary, so it's going to be over here somewhere. Remember, the D represents the distance either one of these planes have traveled. Have either of them traveled 3,000? No, they have not. Though, could we use what's going on here to give us an expression for our distance? Danny seems to suggest we could.
We could,
but you're not sure how. Sure, let's put in speed. Speed is going to be what? The Calgary plane is 450. And the Montreal plane is 550. Now, we got to be careful here. One of these we want to use a variable for, and the other one we want to use an expression for. There's two different ways you can tackle this. It's ultimately up to you how we do this. Where we have to decide though, where do we want to throw down some variables? No, that's not a variable, it's a value.
No, but you wanted to know it in the calculator.
Well, no, but in the distances or in the time section?
The time.
Where do we want to use variables? There's two ways to set this problem up, and it all depends on where you put the variables. In the time? Okay, so Carolyn wants to use variables for time. Carolyn, what variable are you going to use and where are you going to put it? X for both because they leave at the same time. I love it. So then my Calgary plane, the distance it travels is going to be its speed times the length of time. And the Montreal plane is going to be the speed times the length of time. But instead of these distances being equal, what is going to be true about these distances? Sorry?
I was thinking something plus 100 and below 100.
Why are we adding or subtracting 100?
Because I was thinking x plus 100 for the Calgary plane, but that's not going to fit anywhere.
Yes, Presley. These two distances, the distance the Calgary plane flies and the distance the Montreal plane flies, are going to add together to equal what? 3,000, because between the two of them, where they meet, will have covered the 3,000 kilometers. So what we're going to do in a passing type problem, we're going to use our expression here. We're going to add these things together, and they're going to equal 3,000. So this then is going to become the expression that we're going to use. This is going to be 450x plus 550x equals 3,000. So that's going to be 1,000x equals 3,000. So when do they pass each other? How do we know it's hours? Because of the units on everything else. The distance is measured in kilometers, and this guy is kilometers per hour, so your time's got to be in hours as well. It's a good question, though. So then to qualify this thing, they pass after 3 hours. Sometimes this will be the question. Other times it'll be where do they pass? How do we figure out where they passed? Let's add a question here. Where do they pass each other? We know it's closer to Calgary. But where? Carolyn. We're going to take the 3x and we're going to shove it into either one of these expressions. It doesn't matter which one we use. So we're going to take the 450 times 3 is going to give us, what is that, 1350? 1,350 what? What? Kilometers. Which way? Or from where? Specifically, which direction? (1,350 kilometers east of Calgary is where they're going to meet. So if I'd asked you this piece first, where do they pass each other? You could have still set this up in the exact same way. Put your variables in here for t, solved for the length of time, and then plugged it back in. There is another way to do this exact same problem. What if instead, I'm just going to slap this thing down here real quick. What if instead I had put variables in? This is going to be the Calgary plane. This is the Montreal plane. There's my D. There's my V. There's my T. This is still 450. This is 550. If instead I had put my variables in here for D, let's say I call the Calgary plane distance X. What would my Montreal plane distance be if my Calgary plane travels X kilometers right here? If that's X, what's the rest of this? No. 3,000 minus X, right. Because the whole distance is 3,000, the Calgary goes X. It's like the coin problems, right? If I have 50 coins and I have D dimes, how many quarters do I have? 50 minus the number of dimes. So my total distance is 3,000. My distance here is X, so this then must be my total distance minus what's already been dealt with. So if I chose, instead of using time for my variables, I'd use distance. This is how I would have had to set it up. It's going to be 3,000 minus X. And then for my times, I would need an expression here involving distance and velocity. Well, T equals D over V. So then this one's going to be X over 450 equals 3,000 minus X over 550. And in this case, what is true of these two expressions? They have to be equal. Why? Because the time is the same. Love it. So it's going to be X over 450 equals 3,000 minus X over 550. And this then you would have to solve using the same techniques we did before. Multiply both sides by the lowest common denominator of 450 and 550, which is just going to be 450 times 550. They cancel, you distribute, you solve for X. So there's two ways to solve this problem, and it is completely dependent on where you choose to put your variables. But you got to be real deliberate. If this is where my variable is going to go, what does that mean? If my variable here was X, then my variable here has to be X, then we can get a much nicer looking expression. If I had chosen to put my variable for distance, the expression's a little bit more gross, but still something you guys have the techniques to solve. Cool? Question, comments, concerns? The only way you're going to get a handle on this is by trying a whole bunch of these things. I have done two relatively simple examples, but they will not always remain this simple. For example, what they could have done to make this question more difficult, what could I have done? One really tiny change makes this question just a little bit harder. Sorry, Tenmi? If they did not leave at the same time. I could have done that, and you're going to have to deal with that in the style of problem. So I could say, well, they're going towards each other, but this one leaves, half an hour after this one leaves. When do they meet, or where do they meet? You'll have to adjust then your time variables to compensate. There's another way I could make these style of questions more difficult. In one of these problems, actually in this problem, we looked for both, we solved for both time and distance. I haven't given you any examples where we have to look for velocity or speed. Same thing. I could instead set this thing up such that you have to find V. You won't always be given V. I could say that this one is traveling at some speed and this one is going 100 kilometers faster. Then this is going to be the variable that you're going to throw down. So there's a whole bunch of different techniques, but the way you think this thing through isn't going to change. It's the same procedure every time, and you got to be real deliberate. The only way you're going to get good is to practice. So let's try some. I am happy to assist you. Got lots of time. There's 35 minutes left in class, and so I'm going to do a lot of floating. I'll help you where we need it. Yeah. We're going to get you guys to do up at the top here 1, 3, 4, 6. No, I lied. We're going to do 1 to 6, 9 to 12. We're not doing 7 and 8. I mean, we could do all of it. You know what? Forget it. I know you just wrote it down. We're going to do all of it. I want you to play with it. And now I'm definitely not changing it again. You got lots of time. I want you to... Sorry? That is your homework. That's it. Those 12 questions. That's all I'm giving you. As I said, I'm happy to assist as much as is necessary.